So, a very warm greeting to all my dear friends. Today, we'll discuss about today in this lecture we are discuss about the functions continuity and finite constants and that Schrodinger wave equation. This is the third part of our quantum mechanics series for CSBS channels. In the previous lecture, we have discussed about the Heisenberg uncertainty principle and its applications. So, without wasting our time, let's get started. But let's start because today we'll end this series. Let's start with a quote that uh, I feel envious of people who rest. I feel jealous of people who don't want to be successful because success doesn't comes to you until you are completely restless. You have to be. So this beautiful quote. Let's get started. Let's get started to be restless in our life. Uh, so The first topic is function, continuous, and finite constant. So let's suppose fx is equals to x cube. So function to operate operators. So basically, function is a term which is basically depends on something another other term. Okay, you can say it like that. So if we are talking about a function of a, let's say a is a vector or anything. So we denote as a cap. It's called cap. Okay, a cap is equals to d upon dx basically. So a cap of fx is d upon dx of what is fx x cube. So d upon dx of x cube, which is equals to the differentiation equals to 3x square. So, like that only e to the power ax is equals to a cap is equals to differentiation that a into e to the power ax. Anything that lies in the power of e, that is ax, the differentiation remains the same, but uh, the something else that terms anything that term is will be the in front of e. Let's move to the momentum operator. So according to classical theory, one dimension classical theory, we can say that momentum operator is a with this is a classical equation. Del square y upon del x square, this is 2 degree differentiation is equals to 1 upon v square del square y upon del z square. Basically it is a experimentally derived quantity. uh, Through this quantity we can derive this general equation of this equation, that is y is equals to a e to the power minus I omega into t minus x upon v. This is the general equation for this one-dimensional classical theory. Here the omega is angular frequency, I is the constant iota. But why it is I used? I is used for the betterment of the calculation or the ease in the calculation that we have to done in the do in the further questions numericals or say. So after solving it, we know that omega is equals to 2 pi mu, where mu is equals to, where v is equals to mu lambda and E is equals to h mu. It is a particle energy of a particle and energy of a photon. Okay, omega is omega is equals to E upon h and lambda is equals to h upon p. After putting this three terms in this equation, we get this this equation. Y is equals to uh, like this. Y is equals to a e to the power minus I into 2 pi e upon t. Here 2 pi h, this 2 pi h means h bar, as h bar is equals to 8 minute. Yes, h bar is equals to 2 pi upon h. Yeah, this is 1 upon h bar is equals to 2 pi upon h. H bar is equals to h upon 2 pi. So through this basic concept, basic calculation of this concept, we can easily say that y is equals to a to the power minus I upon h bar into et minus xp. Okay. So according to wave function, if we are discussing this y means displacement. Displacement can be in different dimensions like px, py, and pz. And so if we discuss about the function of which is valid for the all the three equations, let's suppose for any one direction, only one dimension. I say any one direction. Let's suppose in x direction there is px. So this is psi is equals to, it says psi, it means psi. Okay, in the further upcoming lecture we will discuss what is psi. So psi is equals to a e to the power I by h bar into et minus x px. That's partial differentiation with respect to x. D psi upon dx is equals to partial differentiation. After this much partial differentiation, we'll get this expression like this. Uh, like this. We'll say it is the psi we have taken here. The same expression will come here. We'll put it in the value of psi. So d psi upon dx is equals to I px h bar into psi. After solving, let's px will go there, and after this much solving, we'll divide multiply I with both denominator and denominator, so that to remove the function of I to betterment of the calculation, for the betterment of the calculation, we get px is equals to minus I h bar upon d by dx. This equation, this momentum operator. After solving this momentum operator, putting it in the value of p single p, representing it as I cap, j cap, k cap, and solving it, we get operator is equals to I d upon dx plus j d upon dy plus k cap d upon dz. I is equals to I h bar, that is operator, p ka value. So energy operator, like same energy operator, we can derive through this. We get energy operator like this. So basically, what we have studied till now is in this lecture is not at all important. It is just a tool for calculating the next two derivation we are doing. We're gonna start. Okay. So basically, are the tools for this upcoming derivations. So the first derivation we do is time independent. That is Schrodinger wave equation, which is time independent. So uh, let's start. According to one-dimensional classical theory equation, dy square d square y upon dx square is equals to 1 upon v square d square y upon dt square. So this is the classical wave equation. Okay, generally we represent this equation as a general solution. So y is equals to a e to the power minus I omega t minus x upon v, where x is the displacement, v is the velocity, t is the time, omega is the angular frequency, and a is the amplitude of this displacement of this general wave. So if y is equals to a to the power minus I omega t minus omega x upon v, so why don't we put the formula for omega? Omega is equals to 2 pi mu, mu is equals to uh, v upon lambda, yes. So after putting the value, we cut v, we cancel out the value of v. For any photon, that energy is equals to h mu, and mu is equals to e upon h. So lambda is equals to h upon p. Y is equals to, after putting the value, we got the function y is equals to a e to the power minus I upon h bar et minus x px. Okay, like this. Psi is equals to a e to the power minus I h bar into et minus x px. Uh, Here, according to wave function, this is wave function. Basically, we denote phi as a wave function. What is function? Function is anything which is finite, continuous, and has a single value. Is called function. If a particle of mass m with velocity with the total energy of the particle, that is, total energy is equals to kinetic energy plus potential energy. Okay, total energy is equals to kinetic energy and potential energy. In the previous lectures, we have discussed about kinetic energy. Kinetic energy, we can write it as p square upon 2m, and potential energy we can write as capital V. So for we, as we are discussing about the wave functions, so after multiplying both sides by psi, so E psi is equals to p square x psi into 2m divided by 2m plus v psi. We take it as equation 2, uh, and then that we got equation 1. Where it is got equation 1? Is this equation 1? We'll partially differentiate this equation 1 with respect to x. So on partial differentiation, we get this again. We the all the equation we got as we previously derived in the above momentum operator derivation. All this expression we have derived like this. Here we got the value of this d square psi upon dx square on partial differentiation, and again differentiation. Again, what we got in partial differentiation, we again differentiate it, and we get the value of d square psi upon dx square is equals to minus uh, px square upon h bar ka square into psi. And if we want this value, then we take cross multiplication. like this, and this equation can be uh, put in this equation number 2. So on putting this equation number 2 and taking common out, and the rest will in the multiplication, we got the Schrodinger uh, equation, one dimension Schrodinger wave equation, that is d square psi upon dx square plus 2m upon h bar in e minus v psi is equals to 0, where d square psi upon dx square can be represented as d square psi upon x square, d square psi upon y square, d square psi upon z square, which is plus 2m upon h bar is equals to h bar ka square is equals to e minus v psi is equals to 0. So this equation we can say it as operator square psi plus 2m upon h bar is equals to e minus v psi is equals to 0. So this is the equation for Schrodinger first wave for one dimensional Schrodinger wave equation, time independent. Okay, so next is time dependent Schrodinger wave equation. So according to wave equation, we already derived that psi is equals to a to the power minus e minus I a to the power. Okay, Schrodinger wave, according to wave equation, we have already derived that psi is equals to a to the power minus I upon h bar e t minus xpx. So if the particle of m is of mass and v velocity moving with x direction, total energy of the particle is equals to kinetic energy plus potential energy. E is equals to 1 upon 2, that previously derived at p square upon 2m plus v. On checking the wave function, E psi is equals to p square x psi plus 2m plus v psi from equation 1. After this is equation number 1, we differentiate with respect to x. So on this on the differentiation with respect to x, the x terms will be in front of here, in front of this, and this term will remain the same. You can see it in the notes. So after differentiation, this term will come here. Again, this is the differentiation of first differentiation. Again, we differentiate it. So d square psi upon dx square. Then again it comes and it 1 I px h bar ka whole square psi, and this is called as psi. So we this all of these terms we have derived in that operator unit. You can check it out. So I square is minus 1. So we put it in there, and we get the value of p square x psi, that is minus h bar d square psi upon dx square. This is equation number 3. Then this we can put this equation number 3 within equation number 1, that is the energy function, this energy equation number 2. But before that we have to differentiate this again with respect to time, because we are depending, we are doing it, there is time dependent. So we have to differentiate equation number 1 with respect to time. So partial differentiation of equation 1 with respect to time, we get a simple equation of this, that d psi upon dt is equals to minus e, this type of equation. We get this after differentiating it, and this is the value of psi itself. It is psi itself, nothing more. And we got the value of e, and then we put the value of 3 and 4 that we got after differentiation. We put the value on equation 2. So I h bar is equals to d I h bar into d psi upon dt is equals to this equation. So what is this? This is a one dimensional time independent Schrodinger wave equation. One dimensional time dependent Schrodinger wave equation. If I read the equation, you may be uh, it maybe seems to be awkward, like I h bar d psi upon dt is equals to minus h bar square upon 2m into d square psi upon dx square plus d square psi upon dy square plus d square psi upon dz square plus v psi. So we can conclude it like I h bar d psi upon dt is equals to minus h bar square upon 2m operator square psi plus v psi. So here it is the one-dimensional time-independent Schrodinger wave equation. Now let's start to our new topic, that is free particle, not three particle. It's free particle in a box. So uh, free particle in a box. Okay. So we suppose a box of In x direction it is a distance wider, in b it is b distance, in y direction it is b distance taller, and it is c distance in z direction. It is a box. So consider a single particle, consider a particle moving in the box. The particle has a potential energy inside the box is zero. So the potential energy inside the box is zero, completely zero. But the ball is perfectly rigid, and hence the potential energy increases. If the ball moves here to here, the potential energy will remains inside, will remain zero, but the potential energy is continuously increases. Okay, so from the three-dimensional Schrodinger wave equation, what is here? It is a one-dimensional Schrodinger wave equation, and if we, because we are discussing about the factor of x, but if we are discussing for x, y, and z, it becomes three-dimensional Schrodinger wave equation. So from three-dimensional Schrodinger wave equation, here don't be scared of this equation. It is just one in the same term, just written in x, y, and z direction simultaneously. But it is just the same term. It is d square psi upon dx square. On equating it, we suppose an wave function in terms of x, y, z. We name it as x, 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 y, x, x, y, y, and z, z, and multiply and put the value of this expression in the value of this psi. So we get d square xx yy zz, d square xx yy zz, xx yy zz, and this potential energy, as in the box the potential energy is equals to 0, so v is equals to 0, 0. Okay, after solving what we get differentiation of x, it is 1. So y square, y and z remains uh, in the numerator. So dividing all this all this side by x x y y and z z, what we get? We get 1 upon x x d square psi d square x bar x plus upon dx square plus 1 upon y y into d square y upon dy square, and like this equation. And here it is e, here it is in three dimension, here e is in one dimension, so we put e in three dimension. So e can be written as ex plus ey plus ez. So this is for x, this is e is for x, and this expression is for x. Why don't we equate it as a one-dimensional term? So let's suppose 1 upon x bar, this single term belongs to k1, and is k1 belongs to e1. So k1 is equals to ex minus 2m h bar square is into ex. So after getting in LHS, we get this equation. After putting the value of k, we get and common 1 upon and common out x x, we get the expression like this, and x x will become 0 due to cross multiplication. Then d square xx upon dx square plus 2m ex xx upon h bar square is equals to 0. This is for x, this is for y, and this is for z. So after this much uh, calculation, we got the value for x-axis, y-axis, and z-axis. What is the uh, what is the uh, what we say? What is the wave function of this, of the particle in x direction, y direction, and z direction? So general equation, we can write generally equation for this, for the solution, general solution for this equation, that x is equals to a sine bx plus c, here where a b c is constant, and here the psi represents the particle's displacement inside the photon. That if you remember that the formula, here this represents the particle, this represents a particle, so the psi represents this displacement in the particle inside the photon. And psi square is the probability of finding the electron. In some cases it is 0, if it is 0, then xx is equals to 0, then x is equals to 0, then a sine bx plus c is equals to 0, then bx plus c is equals to 0, then c is equals to 0, then c is equals to 0. This is the equation. Otherwise, if the position of the particle x is equals to a, if it is a, then a sine b into, in place of x we get a plus the c, the value of c remains the same, just 0. So sine ba is equals to 0. So ba is equals to n1 pi. It's a positive integer n1 pi. So b is equals to plus minus n1 pi, and that xx, the equation we have write as general solution. X is equals to a sine bx plus c. We write it as a sine b, and in the place of c we write 0. So we got an important result that xx is equals to a sine n1 lambda x upon a. So this is the equation for uh, that free particle in a box. If we say about normalization condition, so it is a condition to normalize all the equations that we have studied, and the proper representation of that probability of finding the electron is psi and psi square. So psi square is always in mod. So we are doing here integration. This integration means that we are taking volume. We are doing the integration in terms of volume. So volume integration of this psi square, psi mod of psi square is equals to 1. Here we use mod because the probability can't be negative. Okay, because psi is the the probability to find the electron, the maximum probability to find the electron, but psi can't be negative, so we put it as mod and taking the square of it. Okay, so psi is equals to x, and after 0 to 1 integration of it, this volume integration of it, we get equation like this. After putting the upper limit and lower limit, we get a simple equation like this. It's very simple. This all equation turns out to be 0, nothing else. A square is equals to under root 2 by a, and we put in this in the general equation that we have derived, the general equation here, and we get the equation for the both for all the three axes, that is x-axis, y-axis, and z-axis, all the three axes. Now let's accommodate all these three axes in one equation. So basically what we have find in this three equation and this a, let's accommodate to a single equation. In this equation we have studied, this is a uh, uh, the equation which we have derived from the free particle in that box. All these three equations are accommodated in the single equation. We get a final result that ex is equals to n1 square h square upon 8 ma square for y1, and 2 square h square upon 8 mb square for z, and 3 square h square 8 mc square, where n is the number of order, and this e is equals to ex plus ey plus ez. The whole equation can be represented as this. So in this way we have studied all the quantum mechanics of uh, engineering physics for computer science. The next unit will be soon uploaded in this channel. Make sure you hit that bell icon, you subscribe the channel, you share our videos, and thank you and have a nice day, and thank you for seeing the video. Let's meet in the next video. Till then, keep studying, stay safe from COVID. uh, get your uh, hard work, and put your hard work in your in your goals. Just follow your passion, go for your dreams, and have a nice day.